So we know what a set is. We know that sets are a collection of objects. They're going to give us a collection of numbers. We know that each term in it is a member or an element. And so when you look at your sets of numbers, you will have elements within the sets. And sometimes you will have sets that don't have anything. In this case, they've given us 2 sets. Couple things about sets when we're talking about numeric sets. They are typically labeled with a capital letter. You see this is set A. This is set B, capital letter. They then have an equal sign. So set A consists of is what that equal sign means. And then they have these little squiggly brackets that you probably need to practice writing because nobody likes to write those, but that is set notation, those little brackets that look like that. And then they have listed in A 1, 3, 7, 8, and 10. They have listed in B 1, 4, 6, 10. That tells you the elements that are inside those particular sets. So your sets will always be labeled with a capital letter, typically when you're talking about numeric sets. And then you will have an equal sign and the squiggly looking bracket. Now, sometimes they will label them with a description. So like if I were saying Algebra 1 students, I would probably say Algebra 1 students equals, and I would list all of your names, right, with commas in between each element. All right, the comma in between each element helps you know that I am talking about 1 and 3, not 13. So if I didn't have a comma in between the 1 and the 3, someone would think then that the number 13 was in my set. So you're going to distinguish them by commas in between each element. Then we come to another notation. This little strange looking E means that that is an element of the set. You see that they have 7 and then this notation. That means 7 is an element of A. 7 is an element of A. So then what do you think this guy means? It's not an element, right? It's not an element. All right, so yeah, it is not an element. And so you can see that that is true. If I look at set A, 7 is in set A. So I would say 7 is an element of set A. If I look at set B, you can see 7 is not listed in B. So you would say not an element of B. All right, and then we have 2 sets. And so you can do some functionality within the sets. The 2 things that we're going to look at right here are called union and intersection. They mean really what they mean in any other form. Union, it means to put them together. All right, so if I would say the union of Algebra 1 students with Algebra 2 students, I would put all of those students together, okay? And so the union just puts all the elements of those 2 sets together. What you do not do with union is you do not repeat ones that are in both, okay? So if I were to list A union B, I have 1, 3, 4, 6, 7, 8, and 10. 1 and 10 are both in A and B, but you'll notice I did not list them twice, okay? I did not list them twice. So union puts the sets together. Union will say it's all of them that appear in both sets, okay? Put all the sets together, but do not repeat your numbers. You'll also notice something about sets when you're talking about numeric sets. They put them in order. They put them in chronological order. So we have 1, 3, 4, 6, 7, 8, and 10. That is the union. We also have another notation that they just gave us. Union is noted with this thing that looks like a U. He should be easy to remember. Union looks like a weird shaped U, okay? And so I'm not going to say what is the union of these 2 sets because I'm a math person and I don't want to write that many words out when I'm giving you instructions. I am simply going to write A with that notation and B. And then you're going to tell me what that is. What is that set when I put A and B together? Union puts them together, okay? So then intersection, that's my next term here. Intersection we use all the time, the intersection of Ashley Phosphate and Dorchester Road. If I were to say that, you would all know what I meant, hopefully, right? It's where the 2 roads cross over, right? So if I'm on Ashley Phosphate, that is one set, right? And if I'm on Dorchester, that's another set. If I were to union those 2, that would be 2 really long roads, okay? But if I were to say the intersection of those 2, that is a specific point. That is where those 2 roads cross over, okay? And so intersection is where the 2 sets overlap. In this case, that 1 and that 10. It is the numbers that end up in both sets, okay? Both sets. And this notation looks like the union notation just upside down. All right? So we have the union notation upside down. That upside down looking U is intersection, and that is where the sets cross over. It's where they cross over. Now, in the world of terminology, like if I were to just say it in words, you could say union, but it also means or. So this I do not think they wrote in your book, but I'm going to tell you. So union is written out or. So if I said it's in set A or set B, then I could look at all the numbers together and it would be true. All right? Intersection means and. And means it must fall in both. All right? So intersection means and. It has to be in A and B, right? One is in A and one is also in B, right? But three is in A or B. If I looked at A or B, meaning all of those numbers, A or B, then 3 falls in or, not and. I could not say and with 3 because 3 only falls in A. All right, and so when you look at terminology, we'll start doing this in some logic and geometry especially. You have ors and ands that throw in there as well. All right, any questions on notation? All right, so let's look at this term subset, and then we're going to do all of these together. Subset is kind of what it sounds like. It's another set if every element of the first is contained in the second. All right, and they give you a picture here with circles. So how many of you have done Venn diagrams in like an English setting? Venn diagrams, have y'all done those, right? Sometimes they're done with characters. Sometimes they're done with different pieces of literature, right? And they'll draw circles and you're like, okay, this is over here, this is over here, this is where they're both, right? And that's a Venn diagram. And so they've kind of done this with subsets. That's exactly what this is a Venn diagram. Subset means that every single element of A falls inside B. Now, it's not vice versa, so that doesn't necessarily mean everyone in B is in A, but it does mean that every single element is in B. Subset. They have also given us another notation. You'll notice that over here, we have A, and then this little sideways U with a line under it, B. All right? A is a subset of B. That is what that notation means. A is a subset of B. All right? So let's do a few of these together, and then we're going to do some on our own. So let's look up here at the top, example 1. The first thing they're going to do is they're going to use these two sets, set C and set D, and they want us to do two things with them. What do they want us to do in A? Union or intersection? What is that notation? Union. That means put them together, okay? And so when I write this out, I'm going to write this in set notation. I'm going to say the C union D, and then I'm going to write the equal sign, and I'm going to write my little bracket. And then I'm going to list all those numbers numerically that are in C and D. So 1, 2, 3, 4, 5, 6, 8, and 10. All right? I'm going to list all of those. 1, put commas in between it. And that is my union. That would be my answer. C union D would be all the numbers, 1, 2, 3, 4, 5, 6, 8, and 10. All right? Intersection. These are going to be the numbers that are in both sets. So when I look at this, again, I'm going to write the intersection. I'm going to write my equals in my bracket, and then I'm going to look up here. 1 is only in C, so that's not going to be part of it. 2, well, you can see that 2 falls in C. 2 also falls in D. So 2 is part of my intersection. 3 is only in C, but if I look at 4 falls in C. 4 also falls in D. 5 is only in C, but if I look at 6 is in both of those. And so that is my intersection. Now, just like with the subsets, I can actually represent this with a Venn diagram. All right, so with Venn diagrams, what you're going to do is you're going to draw circles for every set. And you want to make sure the circles overlap so that you can put a place where that little guy right there, 2, 4, and 6 falls. So I'm going to do this. I'm going to draw 2 circles, and I am going to label them based on my sets. So the first one is going to be my C. All right. And then the second one is going to be my D. No, I don't want him shaded. That's okay. Let's do this. I don't want him shaded. So there we go. When you're doing a Venn diagram, you want to label your circles. All right. So you can't assume that I know what you're thinking when you do this. So you need to actually label these C, and you want to label this guy D. All right. And then you want to list all of these. Now it's easiest to start with the ones that cross over. Why? Well, I know where to put those, right? The ones that cross over should likely fall where on this particular Venn diagram? Where you think I'm going to put those numbers? In the middle. That's where they fall. And so I'm going to put my 2, my 4, and my 6 right here. Now, just like with everything else, you don't repeat it. So now I'm going to put the ones that are in C in my C circle and the ones that are in D in my D circle, right? But I've already listed 2, 4, and 6 for both of those guys. So when I list the ones in C, I'm only going to list 1, 3, and 5 right here. And when I list D, I am just going to list 8 and 10. And that is the Venn diagram for this particular one. Now, if it wanted me to shade my answers, I would shade whatever it's talking about. So if it wanted me to shade the intersection, I would shade this part. If it wanted me to shade the union, I would actually shade the whole thing to explain what my answer was. But that is the Venn diagram for those 2 sets. Questions on Venn diagrams? All right, so then if you look at example 2, it's going to use those same ones, all right, those same ones. And it's talking about subsets here, all right? So let's look at A. The question here is 5, 6 is a subset of C. Well, let's look at my Venn diagram if I want to. If I were to have a set that is just consists of 5, 6, is that a subset of C? Does 5, 6 fall inside my C? Yes, 5, 6 falls inside my C, right? And so I would say, yes, this is true. 5, 6 is a subset of C. 5, 6 is a subset of C. Let's look at B. C union D. All right, I've already answered what C union D is. Is that a subset of just C? True or false? Is the union of C and D a subset of just the set C? Yes or no? No, why not? What makes that not true? What's the union? All of these numbers. What's C? Only these numbers. I have a problem. What's my problem? And problem's 8 and 10, right? Do you see that? 8 and 10 is a part of C union D. It is not a part of just C, so this is false. And the reason is I have numbers that don't. C. C is kind of a strange question. Subset means all the elements within it fall inside the other one. So this would mean that all the elements of this would have to be inside this guy. So all the elements of C union D is this, and they're asking, are all of those elements in this? And the answer is no. Okay. C. All right, what is this right here? What does that mean? That was my notation. What's that notation mean? Empty set. They are asking me, is the empty set a subset of C? Are all the elements in the empty set also in C? Well, how many elements are in the empty set? None. So are all of those in there? Yeah, actually it is. So empty set's a subset of everything. Does that make sense? Right? The empty set would fall inside because you could pull out nothing if you wanted to, right? And so, yeah, it is. This is true. Empty set is technically a subset of everything. All right? Look at D. C is not a subset of C. True or false? C is not a subset of C. Now keep in mind, what does subset mean? It means every element is also an element of the second one. So every element of the first one is an element of the second one. And this is saying no. True or false? It's false, right? Obviously, a set would be a subset of itself. Every set number would be in the set. I mean, this is always going to be this is always going to be true. Sets are always subsets of themselves because by definition, they have the set of numbers already. All right, let's look at E. Is 6 a subset of D? This is a trick question, by the way. I'm missing something. 6 is in D, but this is going to be something that you want to check on for a standardized test. Anytime you're talking about sets, you have to be referring to sets. And 6 by itself is not a set because they didn't tell me it was a set because they didn't give me set notation. It's a trick question that they like to ask on standardized tests, by the way, just so you know. If they're asking about, is it a subset, it has to be a set to begin with. In order to be a set to begin with, it has to have set notation. All right, so that's why they're asking that question. All right, I want you to try. So for this one, the first question is, 3 is what? What does that notation mean? 3 is what? An element. Subset doesn't have the line, right? So it is element. So element of B. 3 is an element of B. Is that true or false? That is true. Let's look at B. -2, -1, 1, and 3. If it had subset, it would have been false. Why would it have been false if this had said subset and not element? Because 3 is not a set. It is an element, right? So 3 is an element of B. If this had been the symbol for subset, we would have said no, because 3 is not a set of numbers. It would have to have set notation around it. But it is an element. Element, you don't have to have set notation. We're talking about individual pieces. 21. This is an element of B. An element of B. Remember what I said. Is this represent an element? Does this represent specifically a null set? Does it not? All right, so if you go back to the very first thing we talked about, this represents the empty set, okay? The empty set. The difference between this and this is that without your brackets, 3 is a number, an element, not a set. This guy represents a set. In fact, the other way to write him is this, right? A set cannot be an element, all right? So they're trying to get you to think about the difference between an element versus a set, okay? This by itself is an element of some set. This is a set that only contains the number 3. So when you're using an element, you have to use notation for element. It's an element of, or it's not an element of. When you're talking about sets, you want to say subset or not a subset, okay? So I could never have an element like this with a set notation because that doesn't make sense. He's not a set, he is an element. I also cannot have a set with an element. They have to match, okay? So here I'm talking about an element, so I have to have a notation that talks about an element. Here I'm talking about a set, so I have to have a notation that represents a set. So this is false because this guy's not an element at all. He's a set, all right? Had it been written like this, the answer would have been true because I'm talking about a set, okay? But they wrote it with an element notation. And the null set or the empty set is not an element. It is a set of numbers. I had to use a subset notation there, not an element notation. Does everybody understand the difference between the first one you did, 3 is an element of, and empty set is an element of, and why those two mean something different? All right? So if I have a set of numbers, then I have to use my subset notation. So if I have a set of numbers, I have to use my subset notation. If I have an element, then I have to use my element notation, okay? So you have to know if you're talking about an element is something of or a set is something of, and this represents a set. So this is false, all right? A set cannot be an element of. It can only be a subset. So let's look at the next one. This is a set of numbers, right? 2, 3, and I have set notation. This is a subset notation. So the notation is fine. Now I'm just going to answer true and false based on the list of numbers. The list of numbers up here for C is this. So is this true or false, and why? So the notation is all correct. It is false, and why is it false? There is no 3, all right? There is no 3. All right, let's look at the next one. This is an element or a set? Is 5 an element or a set? Element. Why do I know it's an element and not a set? There's no brackets around it. So, did they use the right notation? They did. They are saying it is not an element. Is that true or false? That is false because 5 is an element, right? So this one is false. About sets of numbers. So we have a lot of sets of numbers, but we're going to deal with all real numbers first. So when you get into like Algebra 2, we'll get into imaginary numbers. Don't worry about that yet. We're going to be talking about only real numbers. Real numbers basically fall into 2 categories, rational or irrational, okay? And so you see that's where my flowchart starts. It starts up here with all real numbers, and then it breaks it into 2 parts, rational and irrational. Rational numbers are the numbers you deal with the most. Any number that can be written as a fraction, all right? In decimal, it's any decimal that is repeating or terminating. So if it repeats 1.33333, all right, it keeps going. Or if it terminates, 1/4 is 0.25, right? So 1/3 is repeating, 0.3 repeating, 1/4 is 0.25. Those both can be written as a fraction, and if you were to look at them as a decimal, the decimal would be repeating or the decimal would stop. Those are rational numbers, all right? That's your larger set that you deal with in like math like this. You also have what's called irrational numbers. Irrational numbers cannot be written as a fraction. When you write them in decimal form, they are non-repeating and non-terminating. The most famous little guy that falls into this category is pi, all right? So if you've dealt with pi at all, like circumference of a circle, area of a circle, all right? So if you've dealt with that at all, that is the most famous. 3.14 is how we write him, but is actually non-terminating, non-repeating. The other ones that fall into this category are square roots that do not have a perfect root. For example, square root of 5. Okay? He does not have a perfect root. If I were to ask you what the square root of 5 is, you would hopefully say somewhere between 2 and 3. Because I know the square root of 4, 2. I know the square root of 9, 3. And 5 falls in between those two. So I know his answer is between 2 and 3, but if you were to put this into a calculator, it's actually rounding it. It is non-repeating, non-terminating. That answer goes on forever. All right? Those are the 2 types you're going to run into most that are irrational. Every other number is rational. So if I were to say square root of 9, that's a rational number because he's 3. If I were to say 1/3, rational number, it can be written as a fraction. If I were to say 2, also a rational number, it could be written as a fraction, 2/1, okay? Every other number is rational. And then from there, we start breaking it down into more specific sets of numbers. The next set of numbers that you get to are integers, all right? Integers. Integers are numbers that are not fractions, so they're whole numbers, right? But they're positive and negative. So -5, -4, -3, -2, 0, 1, 2, 3, and continuing both positive and negative. It is not the numbers in between them. So if you think about a number line, the major tick marks on your number line, those are integers, not the numbers in between them. So 1 is an integer, 2 is an integer, 1.5 is not. 1.5, that's rational, but it's not specific integer, all right? So it's only those whole numbers and their opposites, all right? Which leads us to the next set of numbers, which are whole numbers. Whole numbers are what you think of, 1, 2, 3, 4, 5. It also includes 0. The difference between whole numbers and integers, what do you notice is the difference between the whole numbers and the integers? It doesn't go in the negative. So you'll notice the integers have these numbers, and then they have, what's this guy at the end? These little 3 dots, y'all remember? An ellipsis, right? Which means it goes on infinitely both directions. Whole numbers do not. They start at 0. There is a starting point for whole numbers, and they go infinitely in the positive directions. 0, 1, 2, 3, 4, 5, and so on. All right? And then your most specific set of numbers are natural numbers. These are also called your counting numbers, all right? I have a little one, she's 5. When she was like 2-ish, right? We started counting. And so this is what you learn. You set a set of something in front of the child. They go 1, 2, 3, 4, 5. Those are your counting numbers. What's the difference between my whole and my counting numbers? They both go infinitely in the positive, but what's the only difference between those two sets of numbers?
No 0.
There's no 0 in your natural numbers, all right? So your natural numbers are your most specific set of numbers. Now, if a number is a natural number, it is also a whole number. It is also an integer. It is also a rational, and it is also real. So if it falls into any set, it is also in the sets above it, which is why I like the flow chart. All right? They have written this one other way. What's the other way they have shown me my sets of numbers? That guy, what is he? What's it called? We just did one. We drew it. What's it called when you have circles? A Venn diagram, all right? And so the sets of numbers are often represented in a Venn diagram. You'll notice here your most specific set of numbers is in the center, right? We have natural numbers, and then we have a bigger circle for whole, a bigger one for integers, a bigger one for rational. Actually, they have a box now for rational, and then real includes your irrational and your rational, right? And there are no subsets within your irrational numbers. I want to point one more thing out here. All right, one more thing is they have these weird capital letters, all right? Weird capital letters. This is because math people do not like words very much. We like numbers, okay? And so anytime we can come up with a symbol to represent lots of words, we do. And so that's what these are. For the most part, they are intuitive. By that, I mean you can naturally see where they came up with it. For example, if I look at the very top here, for real numbers, they have something that looks like an R. Maybe like how you would draw it if you were being all artsy and drew little extra lines, but it is an R, a capital R with a little extra lines, real. That seems pretty normal, all right? However, rational. Rational is not an R. It is a Q. Why do you think they would not use an R for rational numbers?
Because
they already have an R, and this would confuse everybody, right? So they just chose Q. Why they chose Q is probably like a Greek for the word rational. I don't know. I really don't know why they chose Q. I'll have to look it up. But Q. Integers. Integers is also not an I. And I'll tell you why. Over here it says Q prime, which means not Q. The other way to write irrational is with an I, by the way. So irrational is actually an I, and that is why integer is not. Integer is Z. Z. And I'm telling you these because some of your questions are going to give you the letter for the number group and not the description, okay? So we have real is R, rational is Q, integer is Z, the other two are normal. Whole is W, natural is N, okay? You will also see this Q prime. It just means not, all right? So when you see that little dash after the letter, it means not. So if it is rational, which is Q, Q with a little dash after it means not rational or irrational. But I will also allow you to use I there for irrational, all right? Those are your number sets. They define rational and irrational. We've already talked about it. If it can be written as a fraction or if it cannot be written as a fraction. Rational and irrational, all right? This first one, A and B. What does that notation in between them mean? Intersection, right? Which means where they cross over, the ones that are in both sets, right? So what numbers fall in A and also fall in B?
1 and 3.
1 and 3. All right. Let's look at 30. C, and what is that second set of numbers? Natural numbers, right? So it's the N with the little extra line. What are my natural numbers? They're also called my counting numbers, right? 1, 2, 3, 4, 5, 6, 7, and so on and so forth, right? Now, if I look at C, this in between it, it's saying union. So it wants us to put the set of C along with all of my natural numbers, right? Most of C falls within my natural numbers, right? There's only one that doesn't. What's the only number in C that doesn't fall in natural numbers? -1. So -1 is going to be a part of my answer, and then every natural number, which is 1, 2, 3, 4, 5, 6, 7, right? And so how I would indicate that is I would start with -1, and then I would put 1, 2, 3, 4, and then an ellipsis. I don't just want to end. I want to keep going. So that ellipsis, that dot, 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 tells me 1, 2, 3, 4, and I'm indicating you're going to keep going in this same pattern indefinitely. And so that's how you'd write that answer. You would include the numbers that are not part of it, and then you would do the set that continues on infinitely, which is that natural number set. All right? And then the last one. What does this symbol mean? Intersection. So I want B intersected with C. All right? What numbers intersect both? Yeah. So there's only one element in that set of numbers, -1. All right? The last thing we're going to do is specifically hone in on just my irrational numbers. Just my irrational numbers. Sometimes people struggle the most with irrational and rational. So we're going to look at just this set, and we're going to see where they fall. All right? So you can call it out. 5, is that rational or irrational? Rational. That is rational, right? I can write it as a fraction, 5/1. So this guy's going to be rational. What about square root of 9? Rational. Rational. It has a perfect root, doesn't it? What is the square root of 9? 3. So I could rewrite this as just the number 3, and that is a rational number. What about square root of 6? Irrational. That is irrational, right? Because I do not have a perfect root there. What about D? It is rational. They do not, this looks like pi, doesn't it? And actually it doesn't keep going correctly, but this looks like pi, but that actually didn't tell me that it continues, okay? And so you can assume that it terminates because they stopped writing it and they didn't give you anything. Now, if they had written the symbol pi, you could have assumed that, or if they had written this little guy with some type of ellipsis that it's going to keep going, then you could have assumed that it's not repeating and it does not terminate. But they didn't give you any of those, and so you can say that this guy is rational because the decimal actually stops, even though it looks like pi. All right? But what about this next one, E? Pi divided by 4. Pi is already irrational. If you divide it by 4, it doesn't make it irrational, okay? It doesn't make it rational, rather. So this guy's going to be irrational. Just because you take pi and you divide it, that's all it's telling you, by 4, doesn't mean it turned it into a rational number. It is still irrational. What about F? It is rational. What does that little line above the 6 mean? Repeating. Rational numbers are repeating or terminating. So this guy is rational. All right? What about this next one? Irrational. There is a pattern. Obviously, there's a pattern, but it is not a repeating, okay? It is a changing. You can see what the pattern is. I mean, it's 1, 2, 1, 1, 2, 2, 1. You can assume this is going to be 4 1s, and the next is 4 2s, right? But that's not a repeating number, okay? It is a changing. It is changing. That pattern is growing, and so this guy here is irrational. All right? Any questions on those? All right, homework. Right here. It is all on page 5. The first 3, they want you to draw a Venn diagram. So you can refer back to where we did the Venn diagram. All of this will be posted, right? Draw a Venn diagram of the number system. So you're going to draw that rectangle with rational versus irrational and your little circles inside of it, right? Natural, whole, integer circles inside the rational box. And then you're going to put these numbers where they belong in your Venn diagram. There's only 3, but you're going to place them where they belong. For 22 through 28, you're going to use those same sets, and you're going to answer those questions true or false. And then for 32 and 33, you're also going to use those same set of numbers, and you are going to do your sets, intersection or union, and tell me which numbers fall into those sets.